Now in this lecture we'll find out the area of the green circle. In the drawing we have triangle ABC to the right angle. Inside this right angle we have those two circles. And our task is to find out the area of this green small circle. In addition, we know that AB equals to 6 units in its length, BC equals to 8 units in its length, the opponent AC equals to 10 units in its length. And our task is to find out the area of this green circle. Actually, the big circle is inscribed by triangle ABC because only if a circle has 3 points of tendency with the triangle, it is defined as it is inscribed by a triangle. The big circle has 1, 2, 3 points of tendencies with the triangle, therefore it is inscribed by this triangle, triangle ABC. While this green circle has only 2 points of tendency with the triangle, therefore it is not defined as a circle that is inscribed by a triangle, but it is defined as a circle that is located inside the triangle. So, first of all, we find out the radius of this circle that is inscribed by triangle ABC. Read again. This is the triangle ABC. This circle is inscribed by triangle ABC because of the fact that it has 3 points of tendency with the circle 1, 2, 3. So we know that the radius of this circle equals to R, and our task is to express the radius R of this circle in terms of the side lengths of this triangle ABC. This is the right triangle ABC. AB equals to A units in its length, BC equals to B units in its length, the opponent AC equals to C units in its length, and our task is to express the radius R of this circle in terms of the side lengths of this triangle ABC. So first of all, we will implement rule 1 in our drawing. I'll pick quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle. This is the radius OM, equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside. So we can actually implement rule 1 in our drawing. In our drawing, point O is the center of the circle, and we define the point of tendency of tangent AB with this circle. This point is point E. Likewise, we define the point of tendency of tangent BC with this circle. This point is point F. We define the point of tendency of tangent AC with this circle. This point is point G. So we join points O and F together by straight line. Point O is the center of the circle. Point F is the point of the circle itself. Therefore, OF is the radius of this circle. This equals to R. The radius OF is equals to R. The radius OF is drawn to point F, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius FO. If BC is perpendicular to FO, it means that this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to rule 1. Likewise, the radius OE equals to R. The radius OE is drawn to point 8. This is the point of tendency of tangent AB with this circle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to the radius EO, it means that this angle equals to 90 degrees inside, And this angle is equal to 90 degrees inside according to the same rule, all 1. So inside this small quadrilateral EOFB, we have 1, 2, 300 degrees. The sum of 300 degrees is 270 degrees, so 270 degrees plus the size of this 4-piece cylinder, total must be equal to 360 degrees. According to the rule, that says that the sum of the degrees in a quadrilateral is equal to 360 degrees. And therefore, this 4-piece cylinder must be equal to 90 degrees inside. So inside quadrilateral EOFB, we have 4 degrees. Therefore, can relate to quadrilateral EOFB is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle EOFB, side EO equals to the opposite side BF. But EO equals to R, therefore the opposite side BF must be equal to R units in its length. Likewise, according to the same rule, in the same rectangle EOFB, side OF equals to the opposite side EB, but OF equals to R, therefore the opposite side EB must be also equal to R units in its length. So in total, we actually found out that the small quadrilateral EOBF is not a rectangle but a sphere because of the fact that all three sides are equal to each other. Each side equals to R. So I write it down. What is the length of this line set AE? A in total equals to AB minus CB again. AB minus CB equals to AE. AB is A, so, and EB is R. So in total, A equals to A minus R units in its length. So write it down. A equals to A minus R units in its length. Likewise, what is the length of this line segment FC? FC equals to BC minus BF. Again, BC minus BF equals to FC. So FC equals to BC, that is B, minus FB, that is R. So in total, FC equals to B minus R units in its length. In the next step, I will present to you rule 2 and we will implement rule 2 in our drawing. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle. This is the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, all two are equal to each other. That is to say, PA equals to P. PA equals to PB. So we can implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common external point, point C, from this common external point, point C, we have two tangents to this circle, tangent CF and tangent CG. And according to rule 2, they are equal to each other. That is to say, CF equals to CG. But CF equals to B minus R, therefore CF must be also equal to B minus R units in itself according to rule 2. Likewise, we implement rule 2 and this common external point, point A. From the common external point, point A, we have two tangents to this circle, tangent AE, tangent AE, and tangent AG. According to rule 2, they are equal to each other. That is to say, A equals to AG in its length. But A equals to A minus R, therefore AG must be also equal to A minus R in its length according to the same rule, rule 2. What is the length of the opposite AC? From the drawing, it is very easy to see that AC in total equals to A minus R plus B minus R. Again, AC in total equals to A minus R plus B minus R. So I write it down. AC equals to A minus R plus B minus R. So AC in total equals to A plus B. Minus R is minus 2R. So in total, we found out that AC equals to A plus B minus 2R. But AC equals to C units in itself according to our definition. So we substitute AC by C. We get that C equals to A plus B minus 2R. Here we subtract C from the equation and we add 2R simultaneously. And we get that 2R equals to A plus B minus C. Here we will divide this equation by 2 and finally get that the radius R, that is the radius that we are looking for, the radius R of this circle that is inscribed by this right triangle ABC, it is equal to A plus B minus C over 2. That is to say, we found out that the radius of any circle that is inscribed by a right triangle, this is right triangle ABC, that could be any triangle, the radius R equals to the sum of the two perpendiculars of this right triangle ABC, that is to say it is A plus B minus the length of the hypotenuse that is C minus 2. And again, the radius of any circle that is inscribed by a right triangle is equal to the sum of the perpendiculars of the right triangle that blocks the circle minus the hypotenuse over 2. So we use this new formula in order to find out the radius of this circle that is inscribed by triangle ABC. Repeat again, the big circle is inscribed by triangle ABC. The green circle is not inscribed by the triangle ABC because of the fact that it has only 2 points of tendencies with the triangle. We have a circle is inscribed by a right triangle only and only if it has 3 points of tendencies with the triangles. If this big circle, we have 1, 2, 3 points of tendencies. So we can find out the radius of this circle according to the formula that the radius of any circle that is inscribed by triangle ABC equals to A plus B, that is the sum of the two perpendiculars of the right triangle, that is most the circle, minus the length of the hypotenuse over 2. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent BC with this circle. This point is point E. We define the point of tendency of tangent AB with this circle. This point is point F. We define the point of tendency of tangent AC with this circle. This point is point G. And we define the point of tendency of tangent AC with this circle. This point is point H. And we define the touching point between those two circles, but we are touching each other externally in this point. This point is point K. So in the next step, we join points O and E together by a straight line. Point O is the center of this big circle, point E is a point on the circle itself, therefore OE is the radius of this circle that we define as R. But actually, we can definitely find out the radius of this circle by using the new formula. Because of the fact that, as I already mentioned before, the big circle is inscribed by the right triangle ABC. And we found out that the radius of any circle that is inscribed by the right triangle is equal to the sum of the two perpendiculars of the right triangle that blocks the circle, that is to say it is A plus B minus the length of the hypotenuse C over 2. Here A equals to 6, B equals to 8, and C equals to 10. So the radius R of this circle equals to A, that is 6, plus B, that is 8, minus C is 10. The length of the hypotenuse is 10, divided by 2. So the radius R equals to 6 plus 8 is 14 minus 10 is 4. 4 over 2 is 2. So in total we found out that the radius of this circle r equals to 2 units in its length. The next step, we join points O and F together by a straight line. But before that, here, the radius OE equals to R. The radius OE is 1 to point E, that is the point of tendency of tangent BC with this circle. Whenever your radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees in size. And this angle also equals to 90 degrees in size according to the same rule 1. The next step, we join points O and F together by a straight line. OF is of course the radius of this circle, equals to 2. Again, the radius OF equals to 2, the radius OF is 1 to point F, that is the point of tendency of tangent AB with this circle. And whenever your radius is 1 to the point of tendency, then tangent AB will be perpendicular to the radius FO. If AB is perpendicular to FO, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to the same rule 1. So in the small quadrilateral FOEB, we have 1, 2 300 the sum of 300 is 270 degrees. 270 degrees plus the size of this fourth missing angle, total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So in quadrilateral FOEB, we have 4 degrees, therefore can relate to quadrilateral FOOB as a rectangle. But you also know that the opposite sides of rectangle are equal to each other. So in rectangle FOEB, side FO equals to the opposite side BE, but FO is 2, therefore the opposite side BE must be also equals to 2 units in its length. Likewise, according to the same rule, the same rectangle FOEB, side OE must be equal to the opposite side FB, but OE is 2, therefore the opposite side FB must be also equal to 2 units in its length. So in total, we found out that quadrilateral FOEB is not a rectangle but a square because of the fact that all of its sides are equal to each other. Each side equals to 2 units in its length. So if you know, this is a square. We define the point of tendency of tangent BC with this circle. This point is point L. We define the center of this circle. This point is point J. And we join point J and L together by a straight line. Point J is the center of this green circle. Point L is the point of the green circle itself. Therefore, JL is the radius of this circle. We define the radius of this circle as x. That is the radius that we are looking for. After we find the radius of this circle, after we find out the radius of this circle, the other green circle will be equal to pi r square, pi x square. And that will be the answer to the question. So the only missing variable is, here is x, that is the radius of this circle, the radius of this green circle. The radius JL is equal to x, the radius JL is 1 to point L, that is the point of tendency of tangent BC with this circle, with this green circle. And whenever your radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius LJ. If BC is perpendicular to LJ, it means that this angle equals to 90 degrees in its side. This angle also equals to 90 degrees in its side, according to the same rule 1. In the next step, we join point J and H together by a straight line. JH is of course the radius of this circle is equals to x. The radius JH is 1 to point H, that is the point of tendency of tangent AC with this circle. Whenever radius is 1 to point of tendency, then tangent AC will be perpendicular to the radius HJ. If AC is perpendicular to HJ, it means that this angle equals to 90 degrees in size. This angle is equal to 90 degrees in size according to the sum rule or 1. So in the next step, we'll join points C and K together by straight line. By joining points C and J together by straight line, you can generate two right triangles. And in the next step, we will prove that those two right triangles can point to each other according to side rule. But before that, we will implement rule 2 at this point C. This comes up point C. It is the vertex of the big right triangle ABC. From this comes up point C, we have two tangents to this circle, tangent CL and tangent CH. And according to rule 2, they are equal to each other. That is to say, CL equals to CH. So we know that CL equals to CH. So in the next step, we prove that those two right triangles can point to each other according to side rule. So, what is on, I have to prove that this is the right triangle edge JC. So we prove that this right triangle edge JC can point to this right lower triangle JLC. So why those two right triangles can point to each other? First of all, JH equals to JL equals to X. They are both the area of the circle, that is equals to X, and therefore they are equal to each other. So it is on JH equals to JL. Again, JL equals to JL, they are both the area of the circle, and therefore they are equal to each other. They are both the area of the circle is equal to X, and therefore they are equal to each other. We only found out that according to rule 2, edge C equals to LC. Again, edge C equals to LC according to rule 2. Again, side HC in the right upper triangle HGC equals to side LC in the right lower triangle JLC, according to rule 2. And finally, this is side JC, this is the common side that belongs to both triangles. So you can write down that JC equals to itself is the common side that belongs to both triangles. And again, JC equals to itself is the common side that belongs to both triangles. So if you found out that those two right triangles can point to each other according to side rule. So what is now if you found out that the upper right triangle HJC, congruent, this is the side of congruent to the lower right triangle JLC, according to side wall. And from the fact that those two right triangles can go into each other, we derive that the corresponding angles are equal to each other. That is to say, those two corresponding angles must be equal to each other in their sizes, according to the rule that says that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore their corresponding angles, that is to say, those two angles must be also equal to each other in their sizes. So we found out that angle HCJ equals to this angle, this upper angle JCL. And again, according to the rule that says that corresponding angles in congruent triangles are equal to each other, we derive that the corresponding angles, those two corresponding angles are equal to each other. That is to say, angle SCJ in the upper right triangle HJC equals to angle JCL in the right lower triangle JLC. So if we define that if one angle is alpha, then the other angle must be also equal to alpha, because of the fact that they are equal to each other. So if angle HCJ equals to alpha, then angle JCL must be also equal to alpha, because they are equal to each other. So if you found out that this is side JC bisect angle ACB. Again, this is side JC, this is the common side, it belongs to both right triangles. Side JC bisect angle ACB. So at the norm, we found out that JC is angle bisector of this angle ACB. JC is angle, here AB is abbreviation for angle bisector. So JC is angle bisector of this angle ACB. Bisect this angle ACB into two halves, each half equals to alpha. JC is angle bisector of angle ACB. In the next step, we will join points. Actually, before that, point O is the center of this big circle, point J is the center of this green circle, and point K is the touching point of those two circles. That is to say, those two circles touch each other externally at point K. Whenever we have two circles that touch each other externally, we can implement rule 10. So, quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. In the moment we have those two circles that touch each other externally, this point P. Point O is the center of this circle, point M is the center of this circle, and the straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass for their touching point, that is point P. of the straight line OM must pass through the attaching point, point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. And put in our drawing, those two circles touch each other at point K. On that we then can implement rule 10. The center of this circle is at point O. The center of this green circle is at point J. And according to rule 10, the straight line that connects the centers together, that is to say OJ, must pass for the attaching point, that is point K. Again, the straight line OJ must pass for the attaching point, that is point K. Or OKJ is one straight line. OKJ is one straight line according to rule 10. So if you join points O and K together, or in J together by straight line, it must pass for point K according to rule 10. So we do it now. It's very easy to see that the straight line OJ that connects the centers of those two circles together indeed passes for point K, that is the attaching point, exactly according to rule 10. If OKJ is one straight line, it means that OJ in total equals to OK plus KJ. Why? Because OKJ is one straight line. But OK is the radius of this circle that equals to 2, according to what we have already found out. While KJ is the radius of the green circle that equals to x. So in total we found out that OJ equals to x plus 2 or 2 plus x. So in the next step, actually we have to join point C and O together by straight line. So we have here point C and point O already joined by a straight line. And in the next step, we join points O and G together by straight line. Point O is the center of this circle, point G is the point of the circle itself, therefore OG is the radius of the circle that equals to 2. The radius of OG equals to 2, the radius of OG is 1 to point G, that is the point of tendency of tangent AC with this circle. Remember, your radius is 1 to the point of tendency, then tangent AC will be perpendicular to the radius GO. If AC is perpendicular to GO, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to rule 1. So actually, we have to join point C and O together by straight line. So we have here point C and O are joined by straight line. So actually, we definitely know that OC is a straight line because we actually join points O and C together by straight line. So because of the fact that we join points O and C together by straight line, OC of course must be a straight line. Okay, so OC is a straight line. Because of the fact that OC is a straight line, we have here those two right angles. So in the next step, we prove that those two big right angles can go into each other according to side rule. Repeat again. We have to prove that those two right angles, that is to say that upper triangle GOC, can go into this right triangle OEC according to side rule. Okay, so now. So as I mentioned before, OC is a straight line because we join points O and C together with a straight line. So we have to prove that the upper right triangle GOC can point to this lower right triangle OEC. But before that, focus on this common standpoint, point C. From the common standpoint, point C, we have two tangents to the big circle. Tangent CG and tangent CE. And according to all two, they are equal to each other. That is to say, CG equals to CE. So we now know that CG equals to CE according to all two. CG equals to CE according to all two. So, the next step, we prove that those two right big triangles can go into each other according to side, side, side rule. So, why those two big right triangles can go into each other? First of all, OG equals to OE equals to 2. They are both the radius of this big circle equals to 2, and therefore they are equal to each other. So, until now, side OG of this upper right triangle OGC equals to this side OE of this right triangle OEC. The both the radius of the circle equals to 2, and therefore they are equal to each other. Repeat again. Side OG of the right big triangle GOC equals to side OE of the right triangle OEC. They are both equal to 2. They are both the radius of the circle. This was to 2, and therefore they are equal to each other. We just right now found that CG equals to CE. CG equals to CE equaling to all 2. And finally, this is side OC, so I mentioned before, OC is the side line because of the fact that we join points OC together by side line. Side OC is the common side that belongs to both triangles. So can I know that OC equals to itself as a common side that belongs to both triangles. So if you found out that those two big right triangles can go into each other according to side, side, side rule. Nothing on. This is the big triangle GOC. And its congruence. This is the same congruent to this right lower big triangle OEC. And from the fact that those two big right triangles can go into each other, we will derive that their corresponding angles must be also equal to each other in their sizes. Those are the two corresponding angles of those two right triangles. So we found out that angle GCO of the upper right triangle, GCO, is equal to this angle, that is angle OCE, in the right lower triangle OCE. Again, angle GCO in the upper right triangle GOC equals to angle OCE in the lower right triangle OEC according to the rule that says that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore their corresponding angles must be equal to each other in their sizes. So again, if we define the size of one angle is alpha, then the other angle must be also equal to alpha. Therefore, this is the third line OC again. The third line OC is the third line by our construction. We're just going point O and C. So OC is also the common side of both those two right triangles. So OC is the angle bisector of the big angle ACB. Why? Because it bisects angle ACB into two halves. Each half equals to alpha. So it is known if you found that OC is also angle bisector of the same angle bisector and angle ACB. OC is angle bisector, AB is equation for angle bisector of the big angle ACB. But we already found out that JC is also angle bisector of the big angle ECB. JC is also angle bisector of the same big angle ACB. And again, we found out that OC is angle bisector of angle ACB, and JC is also angle bisector of the same angle ACB. But because of the fact that angle is only one angle bisector, angle ACB is only one angle bisector, angle ACB is only one angle bisector. Therefore, the angle bisector AB is identical to the angle bisector JC. That is to say, it is one angle bisector. It is the same angle bisector. Angle bisector JC is identical to angle bisector OC. For that reason, those 3 points O, J, and C must be located on the same side line. Why? Because it is the same angle bisector. JC and OC, now the same angle bisectors, the same one angle bisector, and therefore those 3 points O, J, and C must be located on one side line. So points O, J, and C are located on one straight line. Here SL is the projection for straight line. And the straight line that those 3 points are located is the angle bisector of angle ACB. Located on one straight line, that is the angle bisector of the big angle ACB. OCB, OJC is one straight line, and therefore you can say that OC, because of the fact that OJC is one straight line, it means that OC passes for point J. Again, because of the fact that OJC is one straight line, it means that OC passes for point J. Therefore, OC passes for point J. OC passes for point J, or OJC is one straight line. What is the length of this line segment AC? EC in total equals to BC, that is 8, minus BE, that is 2. Again, EC equals to BC minus BE. So now EC, the missing line segment EC is equal to BC minus BE. So EB in total equals to BC, that is 8 according to what is given in the question. EC equals to, in total to EB, that is 8 according to what is given in the question. Minus BC minus BE, that is 2. So in total EC equals to 8 minus 2, that is 6. EC equals to 6 units in its length. And again, this is 97 EC, this equals to 6 units in Islam. The next step, we implement the Pythagoras theorem on this right lower triangle OEC. Here by PT is the operation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This right lower triangle OCE or OEC, the square of the hypotenuse is OC square, and it equals to OE square plus EC square. And again, in the right lower triangle OEC, according to the Pythagoras theorem, OC square, that is the square of the hypotenuse, equals to OE square plus EC square. OE is the missing hypotenuse, so we leave it as it is. OC is the missing hypotenuse, so we leave it as it is. So it is OC square equals to OE square. OE is 2, therefore OE square is 2 squared, this is 4. Plus EC square. We just right now found out that EC equals to 6, and therefore EC square is 6 square. That is 36. EC square is 36, so total, this is the equation, we have 4 plus 36 is 40. So in total, we found out that OC square equals to 40. Here we take a root out of this equation and finding that OC, the missing hypotenuse OC, is equals to the square root of 40 units in its null. 40 is 4 times 10, so we substitute 40 by 4 times 10 inside the root. The root of 4 is 2, so we take 4 out of the root. Inside the root we left only with 10. So in total we found out that the length of the hypotenuse OC is equal to 2 times square root of 10 units in its length. The hypotenuse OC equals to 2 times square root of 10 units in its length. What is the length of this missing 97? 97 JC. From the domain, it is very easy to see that JC in total equals to the hypotenuse OC minus OE. Again, OC minus OE equals to JC. So at the norm, we should find out that the missing 97 JC is equal to the hypotenuse OC. We only found out that the hypotenuse OC equals to 2 times 4 to 10 units in its length. This is OC minus OJ. And again, the length of this 97 JC equals to OC minus OJ. So JC equals to OC. OC equals to 2 times 4 to 10 units in its length. Minus OJ. OJ, according to rule 10, OJ equals to x plus 2. Again, OJ equals to x plus 2 according to rule 10. So in total, we found out that JC, the missing 97 JC equals to 2 times square root of 10. Here we'll open the brackets and get this expression equals to minus x minus 2. So in total, we found out that the length of the missing 97 JC equals to 2 times square root of 10 minus x minus 2. This is the missing 97 JC. This equals to 2 times square root of 10 minus x minus 2. So it is on JC equals to 2 times root of 10 units minus x minus 2. In the next step, we'll prove that the right line OEC is similar to this right line JLC. And again, we prove that the right line COE is similar to this right line JLC. But before that, in this right line OEC, this angle equals to alpha. This angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Well, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So this first missing angle must be equal to 90 degrees minus alpha in its sides. Likewise, in this small right line JLC, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So this first missing angle must be equal to 90 degrees minus alpha. So now we prove that the right line OEC is similar to this right line JLC. So why those two right lines are similar to each other? First of all, this is angle alpha. This is the common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So we found out that all the triangles of the big triangle OEC correspond equal to all the triangles of this small right triangle JLC. Therefore, those two right triangles are similar to each other according to sides, angle similarity rule. So at the end, we found out that this is the big triangle OEC. Is similar. This is the sum of similar to this small triangle JLC. According to side rule. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side OE of the big triangle OEC or side JL of the small triangle JLC is equal to side OC of the big triangle OEC or side JC of the small triangle JLC. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side OE of the big right triangle OEC or side JL of the right small triangle JLC equals to side OC of the big right triangle OEC or side JC of the right small triangle JLC. OE equals to 2, it is the radius of the big circle, it equals to 2. Or JL, JL is the radius of the green circle, that is the radius that you are looking for in this question, and it equals to x, and it equals to OC, OC is 2 times root of 10, over JC, JC equals to 2 times root of 10 minus x minus 2. So in total, we found out that 2 over x equals to 2 times root of 10 over 2 times root of 10 minus x minus 2. Here we have 2 on both sides of this equation, so 2 will get cancelled. So in the next step, we cross multiply this equation. We get that here we have 2 times root of 10 minus x minus 2 equals to x times root of 10. So in total we found out that 2 times root of 10 minus x minus 2 equals to x times root of 10. Here we will add x to this equation and we get that 2 times root of 10 minus 2 equals to x times root of 10 plus x. Here we take 2 as a common factor from those two expressions. So inside the brackets we have left with root of 10 minus 1. Likewise, we take out x as a common factor from those two expressions, so inside the brackets we left with root of 10 plus 1. So today we found out that 2 times root of 10 minus 1 equals to x times root of 10 plus 1. Here we will divide this equation by root of 10 plus 1. And we get that 2 times root of 10 minus 1 over root of 10 plus 1 equals to x. So x equals to 2 times root of 10 minus 1 over root of 10 plus 1. Write it down again. X equals to 2 times root of 10 minus 1 over root of 10 plus 1. So here we multiply both those two sides of the expression by root of 10 minus 1. Root of 10 minus 1 over root of 10 minus 1 is 1. So it is allowable to multiply anything by 1. So root of 10 minus 1 over root of 10 minus 1. So x equals to 2 times root of 10 minus 1 squared. And is equals to root of 10 plus 1 times root of 10 minus 1. According to the algebraic identity, that says that a plus b times a minus b equals to a squared minus b squared. We get that root of 10 plus 1 times root of 10 minus 1 equals to the root of 10 squared, that is 10, minus root of 1 squared, that is 1. Minus root of minus 1 squared, that is 1. So that, minus 1 squared, that is minus 1. So in total in the denominator we left with 10 minus 1, that is 9. So if we found out that x equals to 2, we have root of 10 minus 1 squared, and 10 minus 1 is 9. So in total we found out that x equals to 2 over 9 times root of 10 minus 1 squared. So we open the brackets here and we get that x equals to 2 over 9. Here we have minus square root of 10 minus 1 squared is square root of 10 squared, it is 10, plus 1 squared, it is 1. According to the algebraic identity, that says that a minus b squared equals to a squared plus b squared minus 2 times a times b. So here we have square root of 10 squared, that is 10, plus 1 squared is 1, minus 2 times square root of 10 times 1. And so we found out that x equals to 2 9ths, 10 plus 1 is 11, and we have actually minus 2 times square root of 10. And again, in total we found out that x, that is the radius that we are looking for in this question, equals to 2 9ths. Inside the brackets we have 11 minus 2 times square root of 10. X is the radius of this circle. Our test is to find out the area of this circle. The area of this circle equals to pi times the radius of the circle squared. Therefore, the area of the green circle must be equal to pi times the radius of the green circle squared. This is to say it is pi x squared. Pi x squared. X is 2 over 9 or 2 9ths. Inside the brackets we have 11 minus 2 times square root of 10 squared. To square the radius. It's squared. So today we found out that the area of the green circle, that is the area that we are looking for, the area of this green circle equals to pi. Here we have to square both those two expressions. 2 9 squared is 2 squared, that is 4, or 9 squared, that is 81. And we have 11 minus 2 times root of 10 squared. 11 minus 2 times square root of 10 squared. And it equals to 4 pi or 81, and we have 11 minus 2 times square root of 10 squared. According to the same algebraic identity, this says that a minus b squared equals to a squared plus b squared minus 2 times a times b. We get that 11 minus 2 times square root of 10 squared equals to 11 squared, that is 121, plus 2 times square root of 10 squared is 2 squared, that is 4, times square root of 10 squared, that is 10, and 4 times 10 is 40, so it is plus 40, minus 2 times 11 is minus 22, and minus 22 times 2 is minus 44, times square root of 10. It is minus 44 times square root of 10. So today we found out that the area that we are looking for in this question, that is the area of this green circle, equals to 4 pi over 81, and we have inside the brackets we have 121 plus 40 is 161, minus 44 times square root of 10 square root in its size. And again, the area of this green circle equals in total to 4 pi over 81 times 161 minus 44 times square root of 10. In terms of numbers, it equals to 274.7 square root in its size. Okay, again, we found out that the area of this green circle, that is the area that we are looking for in this question, is equal to either 4 pi over 81, inside the brackets we have 161 minus 44 times square root of 10, square root inside, or in terms of numbers, the area of this green circle equals to 274 0.7 square units in size. So finish with this question. So the next step of some of the lecture. Our task, this question is to find out the area of this small circle. So in the drawing, this is the right triangle ABC. Inside this right triangle ABC, we have those two circles. We know that side AB equals to 6 units in the step, side BC equals to 8 units in the step, and the left of the hypotenuse AC is 10 units. And our task is to find out the area of this small circle. Actually, this is the big circle is inscribed by the right triangle ABC. Why? Because a circle is inscribed in a right triangle or in a triangle only and only if it has 3 points of tendency with the circles. This big circle has 3 points of tendencies with the circle, while this the small circle has only 2 points of tendencies with the triangle. Again, this circle has 3 points of tendencies with the triangle. 1, 2, 3. Therefore, it is inscribed by this right triangle ABC. While this circle has only 2 points of tendencies with the triangle. 1, 2. Therefore, it is not inscribed by the right triangle ABC, but it is located inside the right triangle. So, again, our task is to find out the area of this given circle. In the first step, we found out a general formula for the radius of any circle that is described by a right triangle. This is the right triangle ABC. Side AB equals to A units in itself, side BC equals to B units in itself, and the hypotenuse AC equals to C units in itself. The radius of this circle is R, according to our definition, and our task is to find out the radius of R in terms of the size of this triangle ABC. That is to say, with the expressions A, B, and C. So in order to do it, actually we implemented all 1 and all 2 in our drawing. Point O is the center of the circle, point E is the point of the circle itself, therefore O is the radius of the circle, equals to 1. According to 1, those two areas are right angles. Likewise, we join points O and F together by a straight line. OF is the radius of the circle that is R, and according to 1, those two angles are both right angles. So, in quadrilateral EOFB, we have 1, 2, 3 right angles, and therefore this from this angle must be equal to 90 degrees inside. According to the rule that says that the sum of the angles in quadrilateral is equal to 360 degrees, and therefore in quadrilateral EOFB we have 4 right angles, therefore calculate quadrilateral EOFB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle EOFB, side EO must be equal to the opposite side BF. But EO is out, therefore the opposite side BF must be also equal to R units in itself. Likewise, according to the sum rule, in the same rectangle EOFB, side OF must be equal to the opposite side EB. But OF is out, therefore the opposite side EB must be also equal to R units in itself. So I can find out that quadrilateral EOFB is not a rectangle but a square. Why? Because all of its sides are equal to each other. Inside equals to R units in itself. So this is line segment AE. A in total equals to AB must be, again, AB is A, BE is R, so in total AB equals to A minus R. Likewise, the length of this line segment FC equals to BC must be F. BC is B, BF is R, so in total FB equals to B minus R units in itself. This is the convex point F. From this convex point F, we have two tangents to this circle, tangent AE and tangent AG. According to all two, they are equal to each other. That is to say, A equals to AG. But A equals to A minus R, therefore AG must be equal to A minus R units in itself. Likewise, if we focus on this convex point point C. On the common point C, we have two tangents to this again, tangent CG and tangent CF. According to ortho, they are equal to each other. That is to say, CF equals to CG, but CF equals to B minus R, therefore CG must also equal to B minus R in itself according to ortho. So in total, we found out that AC equals to A minus R plus B minus R. Again, AC equals to A minus R plus B minus R. That is to say, AC equals to A plus B minus R is minus 2R. AC equals to A plus B minus 2R. Here we substituted, we ended 2R and substituted, actually AC equals to C, so we substituted AC by C. AC equals to C according to our definition. So we substituted AC by C and found out that C equals to A plus B minus 2R. Here we substituted, we added 2R and substituted C from this equation and found out that 2R equals to A plus B minus C. Here we divide this equation by 2 and found out that the radius R of this circle equals to A plus B minus C over 2. Okay, the radius R of this circle equals to A plus B minus C over 2. So we found out, we say in general that the area of any circle that is described by triangle ABC equals to the sum of the two perpendiculars of the right triangles minus the length of the hypotenuse over 2. And again, the radius of this circle equals to the sum of those two perpendiculars of this right triangle MC, that is to say it is A plus B minus the length of the hypotenuse, that is C over 2. So we can implement the new formula in order to find out the radius of this circle that is described by triangle ABC. According to the new formula, the radius of this circle equals to A plus B minus C over 2. So R equals to A plus B minus C over 2. A is 6, B is 8, and C is 10. Again, A is 6, B is 8, and C is 10 over 2. 6 plus 8 is 14, 14 minus 10 is 4, so it is 4 over 2 is 2. So we found out that the radius of this circle equals to 2 units in its length. Actually, here we repeated the same process that was already done in this right triangle ABC. We join points O and F together, but point O is of course the center of the circle, the big circle. We join points O and F together by side line. So OF is the radius, which is 2, and those two angles are equal to each other. Both right angles are equal to 1. Likewise, we join points O and E together by side line. O is the radius of the circle, that is 2, and those two angles, the both right angles are equal to 1. So in quadrilateral FOBE, we have 1, 2 triangles, and therefore this fourth triangle is quadrilateral in size. So in quadrilateral FOEB, we have 4 triangles, and therefore get rid to quadrilateral FOBE is rectangle. But you also know that the opposite sides of rectangle are equal to each other. So in rectangle FOEB side, FO must equal to the opposite side BE, but FO is 2, therefore the opposite side BE must equal to 2 units in itself. Likewise, for the sum of the sum of rectangle EOEB side OE must be equal to the opposite side FB, but OE is 2, and therefore the opposite side EB must be equal to 2 units in itself. Those two circles somewhat between them and this point K. So that is to say they touch each other exactly at this point K. Therefore, we can implement rule 10. So, if we implement rule 10, according to rule 10, if two circles touch each other exactly, then the side line that connects them together passes through their touching point. In the line where those two circles they touch each other exactly at this point P. The center of this circle is here at point O. The center of this circle is here at point M. The side line that connects them together, the side line OM. According to this rule 10, the side line OM must pass through point P, that is the touching point. Or the side line OM must pass through the touching point, that is point P. Or OPM is one side line. According to this rule 10, OPM is one side line. We can actually implement rule 10 in our drawing. We put in our drawing. those two circles touch each other externally, this point K. The center of this circle is 0.0. The center of this circle is 0.J. The third line that connects the centers together is of course the third line OJ. The third line OJ must pass through the touching point at this point K. Or OKJ is one third line. Again, OKJ is one third line. If OKJ J is one third line, then it says that OJ equals to OK plus KG. So OK is the radius of this big circle, that is 2 plus Kj. Kj is the unknown radius, so we define it as x. We define the radius of this circle as x. First circle. So total according to rule 10, OJ equals to x plus 2 units in the step. So in the next step, we join point C and J together by third line. When doing this construction, we can actually then we join point J and N together by third line. J is the radius of this circle, that is x. Those two angles are both right angles according to rule 1. Likewise, we join points J and N together by third line. So J N is also the radius of the circle, that is x. According to 1, those two angles are both right angles. So by joining points C and J together with the line, we get those two right angles. So we prove that the right angle JHC can go into this right angle JLC according to side rule. But before that, from the current point C, we have two tangents to this circle, tendency H and tendency N. According to rule 2, they are equal to each other. That is to say, CH equals to CL. The next step, we prove that those two right angles can go into each other according to side rule. So what those two right angles can go into each other? First of all, we just write down that CH equals to CL according to rule 2. And in addition, JH equals to JL, above the other of the second is equals to 2, and therefore they are equal to each other. And finally, CJ is the common side that belongs to both triangles. So if you found out that all the three sides of this right triangle, upper right triangles, are solely equal to all the three sides of this right triangle, therefore those two right triangles are similar to each other according to side rule. So again, if you found out that triangle HJC can point to triangle JC according to side rule. From the fact that those two right triangles can point to each other, we derive that the corresponding angles must also equal to each other in their sides. That is to say, those are the two corresponding angles, and therefore they are equal to each other in their sides. According to the rule that says that corresponding angles can point to angles are equal to each other. Those two triangles can point to each other, and therefore those two corresponding angles must also equal to each other in their sides. So we define this angle as alpha, then this angle must also equal to alpha, so they are equal to each other according to the rule that I mentioned. So total, we found out that JC is the angle bisector of angle ACB. Again, JC is the angle bisector of angle ACB because of the fact that it bisects those two angles to each of them to alpha. So in total, we found out that JC is the angle bisector of angle ACB. So in the next step, we join point C and O together by third line. So CO is the third line according to our construction. And then we join points O and G together by third line. OG is the radius of the circle, that is 2, and those two angles are both right angles according to rule 1. Likewise, we join points O and E together by third line. Those two angles are right angles according to rule 1. So in the next step, we prove that those two right big triangles can go into each other according to side rule. So we found out that the big triangle GOC can go into this right triangle OEC. Why those two right triangles can go into each other? First of all, if here we have, according to rule 2, the common point C, we have two tangents to this circle, tangent CG and tangent CE. According to rule 2, they are equal to each other. This is to say CG equals to CE according to rule 2. Likewise, those two isomers are at the end of the circle. The big circle is equal to 2, and therefore they are equal to each other. And finally, CO is a common side that belongs to both triangles. So we can write down that CO equals to itself is a common side that belongs to both triangles. So if we found out that the right angle GOC, that the right angle GOC convert the right angle GOC convert to this right angle OEC according to side rule. From the fact that those two right angles converge to each other, we know that those two corresponding angles must also correspond to each other and their sizes. So if you find one of them as alpha, then the other one must be also equal to alpha. So in total we found out that COC is the angle bisector of angle ACB. One put bisect angle ACB into two halves, each of equals to alpha. Okay, again we found out that OC is the angle bisector of angle ACB, but we only found out that JC is also the angle bisector of the big angle ACB. JC is also the angle bisector of angle ACB, and we know that angle ACB is only one angle bisector, and therefore those two angle bisectors are identical. That is to say, angle bisector JC is the same angle bisector of angle bisector OC. Therefore, those 3 points O, J and C must be located on the same side line. Okay. You can say that O, J and C, or J, OC passes through point J. Because of the fact that the 3 points O, J and C are located on the same side line, means that OC passes through point J, or JC from the same line. And again, we have that OC passes through point J again. OC passes through point J because of the fact that OCJ is one side line, or JC is one side line. What is the length of this line segment EC? EC equals to BC must be, again, EC in total equals to BC must be. So EC in total equals to BC, that is 8, must be, that is 2. So in total EC equals to 8 1 2, that is 6. EC equals to 6 units in its length. In the next step, we prove that we implemented the Pythagoras theorem on this right lower triangle OEC. This, according to the Pythagoras theorem, in any right triangle, the square of the opposite equals to the sum of the squares of the perpendicular. So in the right triangle OEC, according to the Pythagoras theorem, OC squared, that is the square of the opposite, equals to OE squared plus EC squared. Again, according to the Pythagoras theorem, OC squared, that is the square of the opposite, equals to OE squared plus EC squared. OC is the missing hypotenuse, so in this case, it equals to OE squared. OE is 2, the 4 squared is 4, plus EC squared. EC is 6. According to what we already found out, that therefore EC is 6 squared is 36. So in total, we found out that OC squared equals to 4 plus 36, that is 40. Again, OC squared equals to 4 plus 36, that is 40. OC squared equals to 40. Here we took out all of this equation, and we found out that OC equals to the square root of 40. We substituted 40 by 4 times 10, and then we took 4 out of the root. The square root of 4 is 2. So inside the root we left only with 10. So we found out that OC equals to 10, so times square root of 10 units. Again, OC equals to 2 times square root of 10 units in itself. This is the opposite OC, is equals to 2 times square root of 10 units in its length. What is the length of this 9 7 97JC. Therefore, this 97JC is equal to OC minus OJ. Again, OC minus OJ equals to JC. Again, JC from the drawings is very easy to see that JC equals to OC minus OJ. So JC in total equals to OC is equals to 2 times root of 10 minus OJ. OJ equal, according to 2 equals to x plus 2. Again, JC equals to OC minus OJ. So OC is 2 times root of 10 minus OJ. OJ equals to x plus 2 minus in itself according to 10. So we found out that JC equals to 2 times root of 10 minus x plus 2. Here we open the brackets and we found out that JC equals to 2 times root of 10 minus x plus 2. And again, we found out that JC equals to 2 times root of 10 minus x minus 2. So in the next step, we prove that those two triangles are similar to each other according to side rule. That is to say, we prove that the big triangle OEC is similar to this small triangle JLC. First of all, in the big triangle OEC, this is angle alpha, this angle is a right angle, therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. It is the sum of degrees in any triangle. Likewise, this triangle JLC, this is angle alpha, this angle equals to 90 degrees inside, therefore this first angle must be equal to 90 degrees minus alpha according to the sum of that said that the sum of degrees in any triangle is equal to 180 degrees. Now, it is very easy to see that those two triangles are similar to each other according to side rule. Well, first of all, this is angle alpha, this is a common angle, that is to say, therefore we can write out that angle alpha equals to itself as a common angle that goes to both angles. Likewise, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other, and finally those two angles are both right angles, and therefore they are equal to each other. So we should prove that all the figures of this right triangle OEC are corresponding equal to all the figures this right and JC, therefore those two triangles are similar to each other according to side rule. And again, to the found out that triangle OEC, the big triangle OEC, is similar. This is the side of similar. So triangle JC according to side rule. From the fact that those two triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side OE of the big triangle OEC or side JL of the small triangle JLC equals to side OC of the big triangle OEC or side EC of the small triangle ELC. Again, from the fact that those two triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side OE of the big triangle OEC or side JL of the small triangle JLC equals to side OC of the big triangle OEC or side JL of the small triangle JLC. O equals to 2, JL equals to x, OC equals to 2 times root of 10, and JL equals to 2 times root of 10 minus x minus 2. Here we have 2 on both sides of this equation, so 2 will get cancelled, so we cancel 2. Because multiplying this equation, we found out that 2 times root of 10 minus x minus 2 equals to x times root of 10. So, we have, in this side of the equation, we have added x to this equation, and so I found out that 2 times root of 10 minus 2 equals to x times root of 10 plus x. Here we took 2 seconds from all of this expression, so inside the brackets we left only if square root of 10 minus 1 is equals to here. We took x common factor from those two expressions, so inside the brackets we left only square root of 10 plus 1. Here we divided this equation by square root of 10 plus 1, so we found out that x equals to 2 times square root of 2 minus 1 over square root of 10 plus 1. So here we multiplied both the numerator and the denominator of this expression by square root of 10 minus 1. And so I found out that x equals to, here we have square root of 10 minus 1 times square root of 10 minus 1 square. over square root of 10 plus 1 over square root of 10 minus 1. According to the algebraic identity, we get that a plus b times a minus b equals to a squared minus b squared. Therefore, according to the algebraic identity that I mentioned, a plus 1 square root of 10 plus 1 times square root of 10 minus 1 equals to square root of 10 squared minus 1 squared. So this is 10 minus 1, that is 9. So here we have square root of 10 minus 1 times square root of 10 minus 1, that is actually square root of 10 minus 1 square. So we found out that x equals to square root of 10 minus 1 square over 9. And here we have two nines, and inside the brackets we have square root of 10 minus 1 square equals to square root of 10 squared, that is 10, minus 1 squared, that is plus 1 squared, that is 1, minus 2 times a times b, that is minus 2 times square root of 10 minus 1 times 1. So today we found out that x equals to 2 nines, 10 plus 1 is 11, minus 2 times square root of 10. Repeat again, today we found out that the radius of this is circle, that is the radius that we are looking for. Total is equals to 2 nines. Inside the bracket we have 11 minus 2 times square root of 10. So in the next step we just have to multiply the radius by itself, and multiply it by pi, and that will be the radius of the circle. So the radius of this green circle equals to pi x squared. The radius of this green circle equals to pi times the radius squared, that is associated pi times x squared. So it is pi times x squared. Here we have 9 over 2 squared times 11 minus 2 times square root of 10 squared. And we have here 2 9 squared is 2 squared, that is 4 over 9 squared, that is 81. So this expression equals to 4 over 81. Inside the bracket we have 11 plus 2 times square root of 10. So total x equals to 2 nines, and 10 plus 1 is 11, minus 2 times square root of 10. So total, if you found out that x equals to 2 nines, inside the brackets we have 11 minus 2 times square root of 10. Our test is to find out the area of this ring shape. Actually, the area, and so the area of the ring shape is a circle. So, and the area of any circle equals to pi times the radius of the circle squared. The radius of this circle is x, therefore the area of this circle must be equal to pi x squared. So it is pi times x squared. X is 2 nines. Inside the brackets we have 11 minus 2 times square root of 10 squared. So in total, if you found out that the area of the ring shape equals to, here we have pi and 2 nines squared is 2 squared, that is 4 over 9 squared, that is 81. And inside the brackets we have 11 minus 2 times square root of 10 squared. So here we have 4 pi over 81, and 11 minus 2 times square root of 10 squared, according to the algebraic identity, that says that a minus b squared equals to a squared plus b squared minus 2 times a times b. We derive that 11 minus 2 times square root of 10 squared equals to 11 squared, that is 121, plus 2 times square root of 10 squared, that is 40, minus 2 times 11 times 2 times square root of 10 is 40 times square root of 10. So today if you found out the area of the ring shape equals to 4 pi over 81. Inside the bracket we have 121 plus 40 is 161, plus 44 times square root of 16. And there are some numbers. The area of this circle, the area of this green circle equals to 274.7 square meters inside. Okay, so now if you found out that the area of this green shape equals to either 4 pi, inside the brackets we have 161 minus 44 times square root of 10. In terms of numbers, the area of this circle, this is the area that we are looking for. This question equals to 274.7 square meters in size. Okay, thank you very much.